So I'm going to be reviewing exam question one. Exam one, question four. This is a question that is going over the. It's talking about the preparation reactions of cyclohexanes and 1,2-cyclohexadiene. Um, Basically, for this problem, it's a review and for covering stability factors, and it's pretty important to understand exactly what all of these mean and how they affect stability trends for reactions. The electronegativity means basically how electronegative an atom is, then how easily it is able to take a negative charge, such as oxygen is much more stable in the form of an anion with negative charge than an anion of carbon or nitrogen. The reverse also works with positive charges going towards more positive atoms than negative atoms. So with resonance, it's how many ways that the same molecule can have bonds moved around within itself inter intramolecularly to have stabilization through having multiple different forms of it. And since there would be multiple different resonance forms of one singular molecule and they all contribute to the resonance stabilization, because the more ways it can move around the electrons without having electrons move outside of the molecule lead to stabilization of the molecule itself. Hybridization, it's just generally like how the bonds are in between them. Like sp3 is much more stabilized than s or sp or sp2. So basically, the more types of orbitals that are hybridized together make for a stronger bond and a harder to break bond. So going up, the highest hybridization is much more stable than the lowest hybridization of a singular orbital. Induction basically means that if you're pulling things away from a, a if you have electronegative atoms on one side of a molecule and you're pulling them away from the more positive atoms on a molecule, that's stabilizing because there's going to be an inductive effect on the molecule, meaning the electrons are more likely to be found around the electronegative atom than the more electropositive atom. This stabilizes the molecule because it helps, it's just generally more stable if the electrons are more focused onto a group of atoms or what's called an electron withdrawing group, because then the electron pore region that isn't on the electron withdrawing group is has far less electrons and is less likely to react. Steric effects is a lot less common to have for stabilization because it's just a more specific scenario where a molecule has an atom that is surrounded by a lot of other atoms, say like tert butyl. Tert butyl is a lot less likely to react than like a second degree carbon or a first degree carbon because, well, yeah. Depending on how many bonds it has around it, it's basically just means that it's harder for another atom to attack that atom which has a lot of bonds because there's no way for the attacking atom to reach the electrons of the central atom. Okay, so for this problem, we're looking at this reaction right here, and we're trying to figure out why, if you're looking at all those resonance factors that I just went over, why is this reaction heavily favored in the forward direction? So if we're going to look at electronegativity, it almost seems counterintuitive that you would think that it would be favored in the backwards direction, though it is actually favored in the forward direction. But to see that, you're going to have to go forward a little bit. But you would generally think that it would be favored in the backwards direction if you're only looking at electronegativity, because the oxygen is more electronegative than the nitrogen. If you see in 2, the oxygen bears the negative charge, and in B, the nitrogen bears the negative charge, which seems a little bit counterintuitive. But if you keep looking forward, you can see that resonance stabilization plays an important factor in this. In 2, you can only about move the oxygen's negative charge onto the bond between the ring and the oxygen. So then you could do that, and move the double bond next to the oxygen, just left one. So other than that, there's not much you can really do to have resonance stabilization throughout that molecule. But if you're looking at B over on the right, it has a full pyridine ring, which is very well stabilized by resonance, and it also has the negative charge on the nitrogen. So it's a much larger conjugated pi system that is stabilizing the molecule. So as you can see from that, there's a lot greater ability for B to have resonance factors than 2 if we're just looking at the resonance stabilization. If you're going down in factors for stability, there isn't much of a difference in the hybridization between this. You could look at the hybridization of the nitrogen in A versus B, but that's a pretty small effect of um, SP versus SP2. And that is generally, it doesn't have as much of an effect on the stability of the forward direction versus the back direction as the other factors that we're talking about. And once we're getting down to the inductive effect, this is where you can really see a big difference in why B would be favored over, well, the forward reaction would be favored over the backwards reaction. So you can see that the OS2CF3 that gets moved from A and onto 2, making 4, that that is much more stable on 4 because, well, it's more stable because in the forward reaction direction, it stabilizes 2, gives it more of an inductive effect on that position so that the ring can be more stable due to it having less electrons in the ring. On the flip side of this, you can see that A moving to B has a lot, it still has the inductive effects of the TF group, which is stabilizing the pyridine ring, but not as much as what it had in A, but still, generally between these two molecules, 4 and B, you can see that the stabilization due to the inductive effects and the electron withdrawing groups makes both the rings much less reactive due to electrons being pulled towards those groups. And if you're trying to look at steric effects for this, there is a little bit of an effect on 4 and A, but that is generally not. They're already, you're going to have something which is extremely reactive to react with the oxygens and Fs, and they're pretty unlikely to get knocked off since there's good hybridization, there's some um, resonance stabilization among the SO2CF3 bonds. So basically, that's kind of harder to get knocked off, and the steric effects are kind of less important for understanding the stabilization of this molecule.